Let's do it that way.
Okay, my name is Roger Schlafly. Thank you for inviting me. I'm a quantum computing skeptic, and I'm very skeptical about the whole field, which I'm going to explain here. I do have a blog here that has.
Yeah, he looks great.
Did that should not show up?
Oh,
yeah.
Was that somebody's microphone? Okay, tell you what, anybody can chime in anytime, but chime in intentionally. So mute yourself first and then unmute when you have something you'd like to say. Okay?
Okay, so probably some of you think I'm nuts here, so go ahead and speak up and let me know here. So here's briefly what I want to say. I want to say what I mean by quantum computing. I want to address whether or not it's already been achieved. It's already been achieved. I've been proven wrong already, but I want to address that. And then I want to go into detail on what the reasons are for believing it and why I'm skeptical about those reasons, and talk about some of the investor hype about it. Okay, so if you follow the news, it seems like I'm proven wrong here by a daily basis here. Here's news from just yesterday. There's a company announced that it has a third generation quantum computer. This is a company is worth a Continuum. I never even heard of them. They're worth $10 billion. And this has been reported in reputable publications. This is the MIT magazine. This is the Wall Street Journal. I don't know. I don't know what to make of these claims. Okay, here's the Google announcement from a couple of weeks ago, and they made a claim. And let me go directly to their announcement, if I can do that here. Let me see if oops, I did the wrong one. Yeah, here they were on the cover story. They're the cover story of Nature. Nature is a leading science magazine. They essentially claim to have a quantum computer. Here's their actual paper. Here's their actual paper. The paper, it doesn't quite claim they have quantum advantage. If you look at it carefully, it says it indicates a viable path to quantum advantage. But if you look at, and it got widely reported in the press here, here's the Reuters story. Here's their actual blog where they announced it. So here they announced a verifiable quantum advantage. So I think this title is a little misleading because, first of all, they claim it's a verifiable quantum advantage, and they claim they can solve some real world problems. However, if you read what they have carefully, they have two claims here. One is this quantum advantage thing, and the other is the real world problems. When they get down to the real world problems here, they say it's not yet beyond classical. Okay. Now, what do they mean by verifiable? That's kind of interesting too. You read this and it says verifiable quantum advantage. You think that they've somehow verified that they have a quantum advantage. But no, that's not what they mean at all. You read it, and what they say is they claim they have a verifiable computational outcomes that remain the same when run on different quantum computers. So they claim some other quantum computer could run the same thing and verify what it did. Nobody's done that, but they claim it could be done. And whether it's quantum advantage, apparently the Google people think so, but they were unable to convince the Nature editors of that. Apparently, according to a Scientific American story, the referees were kind of split on whether they had showed some quantum advantage or not. Okay. Sorry, let's go back to my slides here. So they don't claim it's scalable. They don't claim anybody's verified it. They don't claim it's advantage for the useful part. I don't know. I should say that, you know, what a little bit about what quantum advantage is. You probably all know this, but just to make it clear that what I'm looking for and what I'm skeptical about here is somebody who gets together some qubits, scales it up, has some working error correction so it can be scaled, and it does some potentially useful or informative computation that's better than a Turing machine. So I don't really consider something to be if it's just generating random numbers, you know, I don't really get the point of that. Anybody can generate random numbers. I want something that does a computation better than a Turing machine. Okay, so I'm
going to ask you what you mean by better in this case. That's let's narrow that down.
Well, what I mean is it's got to be demonstrably better. You got to convince people. You got to do some calculation where if you were going to do it on a conventional computer, it would take, you know, years or some infeasible amount of time. The example that would really prove it would be, you know, breaking the cryptographic systems, factoring some big numbers, which are believed to take millions of years on conventional computers. If someone were to do that in some, you know, reasonable period of time, a day, an hour, whatever, that would be much better than a Turing machine.
Okay, all right, fair enough.
Okay, so let's. Okay, so another thing that's in the news recently is they gave a Nobel Prize about a month ago, and it seems to me pretty clear these Nobel Prize people, they're itching to give a Nobel Prize for quantum computing and some of these other quantum concepts. Something like half of all the prizes in Nobel physics and chemistry have gone for quantum mechanics in one way or another. And yet, you know, they've never given one for quantum randomness, intrinsic probability, non-locality, action at a distance, things being in two places at once, Schrodinger cats, parallel universes, or quantum computers. So all of those things I regard as sort of unproven fictions. They're things people believe in, but they're not things that have become accepted. The Nobel Committee has a pretty good record of giving prizes to accepted breakthroughs and not to those things. So there are some recent prizes that have mentioned quantum computing. In particular, 2012, 2022, and this year's. So I want to go to the specific announcements to show just what it is they said. So here's the announcement in 2012. It said, enabling their field of research to take the very first steps towards building a new type of superfast computer based on quantum physics. Okay, so they think that's a step towards it. They're not saying it's been done. Here's 2022. Again says research and development utilize special properties of individual particle systems to construct quantum computers. Development is underway to construct quantum computers. Blah, blah, blah. Okay, they're excited. They're following it. They're not saying it's been done yet. Now, this year, they gave it to like 3 people. 2 of them work for Google, or at least one of them previously worked for Google on their quantum computing lab. And Google has been claiming quantum computers for several years. But that's not what the prize went for. The prize went for superconducting tunneling. And here's what they say about quantum computers. They say, one of the techniques being explored in attempts to construct a future quantum computer. So it seems to me that Google people, Nobel people say quantum computer is still an unproven entity. Okay, let's look at some of these previous claims for quantum computing, quantum supremacy. So Google claimed quantum supremacy in 2019. And again, it was in Nature, leading journal. However, this turned out to be not accepted. Let me see if I can go back here. Whoops. Here's what somebody said later, a couple years later. The short summary is now the classical algorithms are 10 orders of magnitude faster than those used in the Google paper. So Google computed something and they claimed it would take the age of the universe to do it on a classical computer, but people found with faster algorithms, it wasn't true. Okay, and then here's this guy, Scott Aronson, one of the leaders in the subject. His comment on this was quantum supremacy can be achieved and then unachieved later. I thought that's kind of interesting. So
just a footnote here. Scott was one of our speakers this year.
Oh, great. Well, well, anyway, yeah, he's an authority on this. Achieved and unachieved later. I don't know how something can be achieved and then unachieved later, but that's what he says. So at any rate, so the point I'm trying to say here is that quantum supremacy, some people claim they've done it. However, it's not been done to the satisfaction of the experts. Okay, now what are the really big quantum algorithms here? I mean, the biggies are Shor's algorithm and Grover's algorithm. I mean, those quantum computer could do those. Those are those where there's really quantum computers have shown to have efficiency gains. And here's a slide from I borrowed from Scott Aronson here. The main applications, first biggie is breaking quantum public key cryptography. The second is simulating physics and chemistry. And then there's everything else, which he says speed ups are not really that great. Speed ups are big for Shor's algorithm, and the others we're not so sure about. And then he says the thing he most cares about is disproving all the people like me who say it's impossible. Okay, so Shor's algorithm. So where this stands is, I mean, some people think it's coming. So the United States NIST standard is on schedule. They are requiring all government suppliers of cryptography to abandon RSA, ECC, and the popular public key algorithms by 2035. Some companies claim they'll already have quantum computers that will kill it by 2030. So you could ask, are companies, what is the progress towards breaking these cryptographic systems? Well, I mean, they factored the number 15 in 2001, and they're still working on 21. Some people claim they've done it, but let me show you a slide that shows some of the difficulties here. Here, this is a guy who says that to factor 15, this is the circuit they used. To factor 21, this is the circuit they need to use. And yeah, nobody's done that. Nobody's done that. So while you regularly hear headlines about quantum computers making all this progress, they're not really making progress on Shor's algorithm. Although people are worried about it, here you have people are worried about it. Here's someone who's worried about it. He thinks we should all stop using these crypto systems now because the quantum crypto companies are going to break it, within about 5 years. Okay. Now, I also like to say that if they succeed, the quantum crypto company, there's no known commercial use to this. There's no, I mean, unless you're in the spy business and you're intercepting, government secrets or something like that, or you're stealing stuff online. There's no legitimate commercial use to Shor's algorithm, to factoring numbers or breaking these crypto systems. Then there's Grover's algorithm, which is even less commercially interesting. It lets you search n items and square root of n steps, but searching is a solved problem. I mean, we have since 1970 or so, we've had relational databases where we could search tables of information efficiently. Around the year 2000, we had indexed the World Wide Web. We can search the whole World Wide Web. And for the last 5 years, we've had these large language models that essentially search all of human knowledge with some human language interface. And I don't really see how Grover's algorithm would ever have any commercial use. Okay, they're simulating chemical reactions. That's possible, but as far as I know, nobody's made any progress on that. I mean, people are skeptical about it. In theory, that chemical reactions follow the Schrodinger equation and, could possibly be simulated, but I don't know. Google succeeded in figuring out protein folding, and they used AI for it. They didn't use quantum computers. And I don't really see much progress towards using quantum computers for that sort of thing. Okay, I want to look at some past claims of progress here. Here we have Nevin's law. Nevin's law came out around 2019. Nevin works for Google. He's one of their quantum gurus. He says the performance of quantum computer occurs at a doubly exponential rate. That means like an exponential to a power exponential. Well, exponential to power exponential is just amazingly fast. Okay, if that were really true, we would have quantum computers by now. I mean, there has been progress in quantum computing technology, but it's not that fast. 2017, Google said machines are only 5 years away from commercial exploitability. Now they're saying they're going to have large-scale, error-free business and scientific calculations by 2029. Well, okay, maybe. Other claims of quantum supremacy. Google claimed it in 2019. I talked about that. IBM claimed it in 2023. Google claimed it again, last year in a Nature paper. And this year, D-Wave claimed it in a science journal. That's the other top journal. I say Nature and Science are two leading science journals. Nature claimed it. D-Wave claimed it. However, that was also pretty quickly shot down. I think I have some references on that.
Who do you think will be next to claim quantum supremacy?
Well, I don't know. They're like everybody's claiming this rapid progress. I mean, I don't think anybody's going to do it. Okay, I think it's impossible. I don't think anybody's going to do it. But I don't know. I think it'll be. I mean, D-Wave has a stock price they have to prop up. Google makes tons of money anyway, whether anyone believes in their quantum supremacy or not. But there are lots of companies now that are specialized in quantum computing that their whole value depends on this. So let me just give an example of here. People are investing in quantum computing stocks. And these companies are worth billions of dollars.
So I have
here's an investor newsletter talking about what here. Google performed a computation 5 minutes. It would take the world's fastest supercomputer longer than the age of the universe. There's a lot of hype about this. Now there are skeptics too. Here's a short seller. We are short sellers of D-Wave, a $2 billion quantum annealing company whose stock has surged, blah, blah, blah. And it says that it seems they have no way of giving any commercial products or selling anything. The stock fell after they criticized its $2 billion valuation. Here's another
Roger,
company.
I remember in the mid 60s, they were saying full AI is just around the corner. Just a couple of years from now. Wait until 1970 and we'll all be talking to machines. And it took decades, but startling progress in 2017 and beyond.
Well, AI is an interesting comparison because AI has also been hyped to a very great extent. But let me show you these companies now. Here's D-Wave. So the shorters were claiming it's way overvalued at $2 billion. As of today, it's worth $9.7 billion. It's only gone up since then. Here's another company, Rigetti Computing. It's worth $11 billion. Here's another company, IonQ. It's worth almost $20 billion. Here's another one. It's worth $3 billion. So, as you say, yeah, maybe it'll take 20 or 30 years. These companies cannot exist like this for 20 or 30 years. I mean, they're going to have to show some results within 5 years or they will be bankrupt. There's investors, they don't wait 20 years. There's no way.
So I have a question. So as you mentioned that it seems like there is no verifiable record of quantum supremacy. But is the point that we haven't achieved quantum supremacy right now, or are you saying that it's not possible? And if you're saying that, why?
Okay, I'm saying what I'm trying to convince you so far is that, first of all, quantum supremacy has not been established to the satisfaction of the experts. Some people say it has, but there's no consensus that it's been achieved. Secondly, I want to convince you that there's a crazy investor hype on this that's crazier than the dot-com boom of the 1990s. There's people investing at it, and these companies cannot possibly deliver on expectations, even if they get quantum supremacy. There's just no way there's ever going to deliver some product that's useful to people, or it just seems completely hopeless to me. But whether or not it's possible, okay, I want to get to that. So I want to talk about the reasons for people believing that quantum computing is possible. So everybody says the start to it was this like 1981 paper of Richard Feynman. And here was his argument. He says quantum mechanics, it can't be efficiently simulated by a classical computer. And but you could possibly build a quantum computer that could simulate a quantum process. And then you would seemingly be doing something that a classical computer could not do. And I want to give you how I visualize this in terms of something called a Galton board. Which I have an illustration of. Let me get it here. Okay, I've lost it at the moment, but I'll find it. So here it is. Here's a Galton board. You have a little ball and you drop a ball down and it hits these pegs and dropped on.
We don't see that right now. We're seeing double slit experiment.
Okay. Let me change this. Let me okay, here you go. Here's a simulation of this. You drop the ball and it hits these pegs. And every time it hits a peg, it can bounce one way or the other. Here's a bigger one. Can you see that? So
we see it.
All right, speed it up and goes faster. So this illustrates a binomial distribution. It comes and hits the bottom, and it's all that. But the point is that each time the ball hits one of these pegs, it could go either way. It could go right or it could go left. And I think the thinking behind Feynman's theory is that this is kind of the way electrons are. This is kind of the way quantum mechanics were. That if you look at the quantum mechanics of an electron or something like that, there are these uncertainties that it's constantly choosing between different paths to go, and it can go in different paths. And because at every stage it's got different paths to choose from, it's after some period of time, there are like exponentially many paths. So if you were to like try to simulate this Galton board and you tried to keep track of all possible paths, it'd be exponential in the number of rows. And it'd be like hopeless to simulate all possible paths if there are a lot of rows, because there are just too many of them. And I think that's the fundamental idea between Feynman thinking that there could be quantum computers, that nature consists of, is kind of a big Galton board in a way, that with particles constantly forking between different possibilities, and those different possibilities are impractical to simulate. Another illustration of this is this game called Plinko, which is kind of the same thing. Whoops. I don't know what that is. Oh, it's an ad. Okay, so it's kind of a gambling game here, I guess. You can drop all these balls, and so the claim is that's what quantum mechanics is like. Quantum mechanics is like a big game of Plinko. Things are like constantly, there are these constant forking paths that happen all the time, and you can't simulate it. Okay, so, and as Feynman explains here, the double slit, oh, I didn't, here, let me change, get to this double slit experiment. So, and this is the way Feynman views quantum mechanics. Here he says the double slit experiment is the central puzzle of quantum mechanics. It's the mystery. Here's how Scott Aronson, shows this in a slide here when he explains quantum computing. Here he says it's probability theory of minus signs. You can have, if you have particle has probabilities that go in here, but in the double slit experiment, these amplitudes can cancel out and you get an empty pattern. And so the double slit experiment kind of shows how quantum computers are possible, because probabilities can kind of cancel out. Things can go in different paths and probabilities cancel out. Okay, so I don't know. Supposedly that's supposed to convince people that quantum computing is possible. The next argument for quantum computing comes from David Deutsch. And he's a big believer in the many worlds theory of quantum mechanics. And he says you look at the double slit, that proves the many worlds theory. Now, the many worlds of quantum mechanics is really kind of a crazy theory. And I don't think, you hear people advocate for it as if the theory makes sense. The theory really doesn't make any sense. I just want to lay it out how crazy it is, because nobody lays out how crazy it is. It really doesn't even have that much to do with quantum mechanics. You can take any theory that predicts probabilities, and then you just come along and say, I don't believe in probability theory. Probability says something might happen and something else might, and then it might not happen. Many worlds theory just comes along and says, no, everything's happening. Everything happens. You say a probability of something, there's no such thing as a probability. All those other things happen. So if you were to watch a Galton board or something like that, or a Plinko board, all those paths, you see the ball that hits a peg and goes one way or the other, they'd say that's not what's really happening. Every time a ball hits a peg, the world is being split up into two worlds. And one world, the ball goes one way, and the other world goes the ball that way. And pretty soon you have these zillions of worlds with all possible paths. And they say each of these split worlds is as real as any other. Now people hear this, they think, oh yeah, but a lot of these worlds are improbable and you don't have to worry about them. But no, that's not where the theory goes. The theory is not able to assign probabilities to the different worlds. They cannot do that. All the worlds are equally real. There's no world is any more likely than any other. They're all real. If you buy into any world's theory, you just have to like forget that probability makes any sense whatsoever. Now, David Deutsch, okay, here's another slide I borrowed from Aronson. Here's how he says. I mean, he's convinced of the many worlds theory by the double slit experiment, but then he says, Shor's algorithm. This is why Shor's algorithm works, is because it's doing a computation that would take an enormous amount of steps or so in a classical computer, and yet Shor's algorithm somehow is going to do it on a quantum computer. The only way it could do that is if his quote ran off my screen, I'm afraid, but the only way it can do that is if it's doing a computation in parallel universes. The universes is dividing up into millions and zillions and 10 to the 50 maybe universes, and it's doing computations in all those different universes, and it's somehow getting merged together.
So are you claiming that quantum computers depend on many universes?
No, I'm not. I mean, there are people who believe in quantum computing who don't believe in the many universes. So no, I'm not claiming that. I do claim that many universes is one of the big reasons for people believing in quantum computing. It was certainly big for David Deutsch. It's big for a lot of people. So no, you can believe in quantum computing without believing in many worlds.
Is there an explanation for, like, even if we forget the quantum computing, just for quantum phenomena like double slit experiments and so on, is there an explanation for that? I mean, some people use many world universe to explain that. So is there an explanation for double slit experiments which is not many world world explanation?
That's a good question. So is there an explanation for double slit without many worlds? The double slit, yes, I'd say absolutely. The double slit, a lot of people look at the double slit, even if they don't buy double many worlds, they say, well, but at least like the photon or the electron or whatever it is in two places at once. And they'll use that as a reason for quantum computing. Something can be in two places at once. However, here's what I say. The double slit experiment, it got discovered 200 years ago, okay? 200 years ago. And, people saw it 200 years ago. They didn't think, the parallel universes. No. Any kind of, they saw it and they thought, okay, that proves that light is a wave. Any wave phenomenon, anything that is a wave shows interference patterns. So anything that's a wave, sound waves, water waves, anything else will have something like a double slit experiment. So I think all the double slit experiment proves is that light or electrons or anything else has wave properties because you can get interference patterns. It does not prove that anything's in two places at once, or parallel universes, or anything like that.
Okay, but isn't it true that, I think people have done double slit experiments where they have sent like one photon or one electron at a time and still have got the interference pattern. Is that not correct?
That is correct. However, I would partially take this issue of one electron at a time. So
Mhm.
when I say I buy into quantum mechanics, here, did I put? I think I had a slide of what I buy into quantum mechanics. So I buy into textbook quantum mechanics. So what does that mean? That means there are non-commuting observables. That means there's wave particle duality. That means that means it makes probabilistic predictions about measurements. Quantum mechanics does all that. But in quantum mechanics, these things like electrons have both wave and particle properties. So an electron is not really a particle. It's just something that sometimes looks like a particle and sometimes looks like a wave. So when you observe it, it looks like a particle. But when you're not observing it, it has these wave properties. So when you say fire one electron at a time, I think from just textbook quantum mechanics, I would say one electron gets emitted at a time, one electron gets detected at a time. However, in between, it's not a particle. It's some kind of wave-like thing that we don't understand. And it can't be a particle. Anything in quantum mechanics can't truly be a particle because of Heisenberg uncertainty. If it really a particle, it would have a definite position and momentum, and that can't happen. It can't happen. It doesn't happen. So when that electron, it can be emitted one particle at a time. It can be detected one particle at a time, but in between, it's some kind of phase. It's some kind of wave that does not have a definite position and does not have a definite momentum. It doesn't have those things until it's measured.
What do you think about quantum entanglement?
Well, what do I think of quantum entanglement? Okay, so the way this popularly gets explained is that you could have two electrons that are entangled on opposite sides of the Earth, and you measure one, and your measurement of one of them causes an effect on the other, and there's a non-local effect because they're entangled. Doing something to one causes something to happen to the other. However, I would say there's no non-local causality that's ever been demonstrated. What you have is a correlation. You have if those entangled particles were created in the same operation, they have properties that are entangled, and it's not really even a big quantum mystery in my view, because you have the same thing classically. If you have two classical particles and you create them at the same time, and from energy conservation, of momentum conservation, that learning something about one tells you something about the other. Yeah, they could be separated, and you could learn something about one and learn something about the other. And there are some correlations there, but there's no action at a distance that anyone has ever demonstrated.
Yeah, but the hidden variables problem isn't in classical mechanics. Am I correct about that?
Yeah, that is correct. So
that adds an extra kind of magic to the entanglement problem with qubits or with electrons.
Well, that's what they gave that 2022 Nobel Prize for. You cannot replace quantum mechanics with a theory of local hidden variables. So whatever that electrons is doing in quantum mechanics, when it's kind of like a wave, kind of like a particle, kind of something with a wave function, whatever it's doing, it's not just values of classical variables that we don't know about.
So I mean, there is some there is some mystery there. There is something going on that's not just classical.
Yeah, that's right. That's right. It does not have a positional momentum the way classical variables would. It can't. You measure the position, you mess up the momentum. You measure the momentum, you mess up the position. Whereas classically, that doesn't happen.
So just to be clear, Roger, you don't think, did I hear you say that quantum entanglement hasn't been demonstrated?
No, I wouldn't say that. I mean,
okay, I misheard you. Sorry.
I mean, they gave the Nobel Prize in 2022 for it. I mean, for experiments that demonstrate entangled particles. However, I mean, they never said. I mean, the thing that's popularly said is that doing something to one particle has an effect on the other particle. They didn't prove that, and the Nobel Committee didn't say they proved that. There's a correlation, but there's not a causation.
Yeah, I mean, I think that's agreed upon. We can't explain it in terms of causation.
Yeah. Okay, so what I'm arguing here is that I'm arguing here is that the reasons for believing in quantum computing are mostly fallacious. I mean, you can believe in it without believing all this weird stuff. But the way it's usually explained from David Deutsch or whoever, it's quantum computing. It's doing something because qubits can have two values at the same time, because something can be in two places at once, because parallel universes, or all these explanations are given, all of which I think are fallacious.
Well, they're certainly unintuitive. I wouldn't go so far as to point to them as being fallacious. And the reason I say that is because we have a lot of results in physics in the 20th century that are absolutely counterintuitive. And if you'd said them to somebody in the 17th century, they would have put you in a loony bin. And yet, these things, relativity, general relativity, quantum mechanics, have turned out to be the reality that we live in. So while I agree with you that these are very strange phenomena, my question is, does that justify our saying, hey, wait a minute, this can't happen. We can't build on this?
Well, I could be proved wrong. Okay. I just think, I mean, I could be proved wrong. I just think a lot of money has been poured into quantum computing for the last 20 years or so. A lot of really smart people have worked on it. They would really like to show some sort of super Turing effect, some sort of computation where it's better than a Turing. They haven't done it. And their main reasons for thinking that it can be done have to do with interpretations of quantum mechanics that I think are not quite right, like many worlds, like non-local effects, like qubits having two values at the same time. We just don't know that any of those things are really possible.
I thought that it was generally accepted that there was an experiment that proved Bell's theorem about the Bell states, which led to the fact that entanglement is a real phenomena. Probably doesn't really, again, intuitively just define how it works. And, for practical applications, I don't think anybody cares, but it had to do with the experiment I'm thinking about had to do with two astro observatory on I want to say the Canary Islands or some remote set of islands out in the middle of the Atlantic, where they were capturing light from a remote quasar or something like that, splitting it, and for long periods of time, and measuring the probability that it would be one or the other, and it proved the Bell's inequality, or it supported it. I'm sorry, again, you don't prove anything with science. It supported Bell's inequality, and that has been generally accepted. But that
No, you're absolutely right. I
Yeah.
think it's hilarious that people even do experiments like that. But all that is, I mean, yeah, and they get the Nobel Prize for that, although those people weren't looking at quasars, but the advantages of quasars is to say that they're trying to like make the common cause, narrow down the possibilities for the common cause to be some distant quasar or something. I mean, Bell really didn't believe in quantum mechanics. Bell had this belief that quantum mechanics could be replaced by a theory of local hidden variables, and that the quantum uncertainties that we see are really just our lack of knowledge about some classical variables. And he had this proposal to replace quantum mechanics with kind of a classical theory. And then he proved this brilliant inequality that showed that a classical theory would have different predictions from quantum mechanics. And the experiments show that that's impossible. No, you cannot replace quantum mechanics with a classical theory. And that means that, I mean, it just affirms what everybody thought from the start, that you have Heisenberg uncertainty, that particles, can't get position and momentum at the same time. You measure one, it messes up the other. You measure the momentum, it messes up the position. You measure the position, it messes up the momentum. So, but you can't just say that position and momentum, they really do have these definite values that could be known somehow. We just don't know them. That theory does not work. So they showed that. Essentially, my opinion, all that Bell stuff, it really doesn't tell you anything about quantum mechanics, except that it cannot be replaced by a classical theory. It does not tell you that anything is non-local.
But it's such a cool theorem. I mean, talk about elegance. Talk about genius.
It is. It's absolutely
well. It's the basis of saying if you have two entangled qubits that are then found at a distance, the Bell state shows that. Again, if you know the state of one, you know the state of the other, which is the entanglement property that things like quantum key distribution use via the teleportation algorithms. So to me, that is a useful, practical thing, a quantum phenomena that's been demonstrated. People are building hardware to, as we speak, to make networks based on that stuff. And it has been demonstrated here in Chicagoland between a lab and a university in the downtown loop. I forget what it is. I want to say 22 miles, but I don't know the exact distance. Over a single mode fiber cable is how they transported the qubit in that case was a photon, and they transported the photon via a single mode, single segment fiber from, I think, Argonne, or might have been Fermi to a university in the Chicago downtown area. I think might have been Northwestern, I'm not sure. But that experiment's been repeated many times by many labs.
That's correct.
Yeah.
I mean, that's absolutely correct. And in my opinion, that's all just a complete waste of time. I don't really see any point in it. Okay.
Well, the point of quantum key distribution is if a bad guy intercepts your key in flight, it's detectable. So there's security value to that.
I don't see why that's of any value. I mean, why do you want to detect somebody trying to hack into your system? I mean, what good does that do you? If so, you detect it. Okay, all that means is you shut down your communication. Why is that useful? Nobody wants to shut down their communication. They want to send secure messages that will be secure, whether somebody taps into them or not.
Well, if you detect it, you can go look for it, or you can use alternate pathways. The big thing about quantum key distribution is it provides a mechanism to use symmetric keys and avoids the whole Shor algorithm and the other quantum algorithms that will break two-part keys. So there is value there. I mean, it's not just me. Nokia and a number of other companies are building these transceivers based on this technology and selling them, to people who are highly sensitive to security issues.
Okay, they are. Okay, let's talk about this for a moment. So if you could, this is another potential application for quantum computers, because if you're using a quantum key distribution, you can't go through a regular router. You'd have to have a quantum computer as your router in order to pass the qubits on to whoever's the next person down the channel.
Absolutely. It isn't perfect. It's just point to point is about all you can guarantee at the moment. Yes, that's absolutely true.
You do it point to point. Is if you have a quantum computer as your router.
Well, I mean, if you're doing point to point, you don't need the routers. You just need the end pieces. And if you need a point to point thing, the first customers were trading companies in the New York and in the New Jersey side of the Hudson River that just wanted a super secure link across the river to the stock exchanges, and they were willing to pay extra for bulletproof, or what they believe is bulletproof security.
And they
Ron,
thought that
Ron, you seem to know more about how this is being used. Is that actually in production right now, or is it just in testing?
I think the one I was talking about across the Hudson has been there's a company that's been selling that for 2+ years. All of the telecoms are trying to figure out their version of this point to point thing, which is not good news, because if they don't play together, it's going to be useless. Because I mean, eventually there will be quantum routers. They'll just be as mentioned, they have to be tiny little quantum machines that can move quantum states around without contaminating them. But the quantum key distribution test that was done, again here in Chicago, we were just at the quantum, Chicago Quantum Summit, and another company claimed they had done something very similar and I forget where they said they did it, but again, it was in the 12 to 22 mile range. It has to be a single fiber, no splices, no equipment in between, which sets that range limit. But people are doing it. Nokia is betting on that people will come and buy their parts. So for short range stuff, now it might be short range stuff still works for like data centers, just to get from one side of a campus to another, for example. But
So what if you do teleportation along the line? Can you use that as repeaters?
well, yeah. So what a quantum repeater becomes is you basically doing a teleport, quantum teleport from A to B, and then now you have this state of the original qubit. But it is, I mean, Barry, you know the algorithm. What is it? The BB84.
Yeah, yeah.
It's not trivial. Um, and so by the time now you got to transfer the key into a super secure thing, or you need to be able to somehow now that you have transposed the state of a qubit from point A to point B, it's not a copy. It's the state because you had to
Right, of
destroy
course. Yeah,
the
yeah.
state at point A, right? But now that you
I'm
have
just
the
saying,
state in the router, if there's a way that you can now route that to another hop, that's the challenge right now.
yeah,
And
it's a
then
challenge. I mean, it's an engineering challenge, but
yeah,
it can be done. I mean, it's in theory, right? We could do that to extend the range of these things.
yeah, absolutely. And then, but what I mean, it just gets uglier and uglier though, because um, how do you do packets and messaging packets and stuff in quantum? You can't label them because of this whole business of once you read the qubit, you've destroyed it. So you can't, there's just a whole bunch of challenges, but a lot of
Yeah, it's
people are selling stuff for point to point, and they are selling stuff. So
and there's tremendous engineering challenges, but I don't even get what the point of it is. Well, first of all, I mean, unless someone is able to build a computer that does Shor's algorithm, secure communications is a completely solved problem. Okay, I mean,
well, bear in mind that people talk about shorts, but there's at least one other quantum algorithm that can break those keys. And it has to do with the fact that quantum computers are based on, especially gate-based machines, are based on gates that are referred to as unitary. And one of those properties is if they are reversible. You can reverse any algorithm. So all you need to do is build a quantum computer that can do the massive multiplication of two prime numbers and just run it backwards. And I actually wrote that program. It was one of the assignments for my D-Wave quantum annealing class, and it works. It was for a small number, but it worked. You just run the algorithm backwards. Crazy
okay,
stuff, yeah.
but I mean, NIST currently has proposed algorithms to replace RSA and elliptic curves that they claim will be resistant to quantum computers. They run in pure software.
Yep.
I mean, they're not as efficient. They're not as known to be as reliable as RSA and elliptic curves, but um,
The key word is resistant.
well,
They're real. They don't want to say proof or safe, and NIST is the only one that actually uses the right terminology, quantum resistance. A lot of people are referring to these algorithms as quantum safe or quantum proof. It's just not true.
well,
But
NIST believes they're resistant, and the NSA believes they're resistant, and they're going to like convert our government infrastructure over to it within the next 5 years.
yeah,
So,
but the key again is that they're saying it's resistant. It's not guaranteed to be fixed.
okay,
So
but I mean, guaranteed. Okay, but this quantum stuff, it's not really guaranteed anyway. You realize this? I just think it's a whole list of fallacies it's based on. It believes you have to like it you know it people you think you can avoid probabilistic attacks. There's a belief that hardware cryptography is better than software cryptography. I mean, I don't think that's true at all. I mean, you can.
Well, hardware cryptography is great until it's cracked. Then it's a huge nightmare.
Well, but hardware cryptography has hardware attacks. So you're sending information down a fiber optics. If there's like errors, if there's like errors in your transmission, you know, you could be revealing information. Whereas like software cryptography, you don't have that problem. You're just sending bits down, and the bits are not revealing anything other than zeros and ones.
Yeah, but the problem with hardware, especially if it winds up in remote locations, is if it gets compromised, your only solution is in general replace the hardware, and that becomes a nightmare. So software is undoubtedly going to be what, you know, like NIST and anybody else interested in doing quantum resilient algorithms. But the thing about quantum resilient algorithms is pretty much, I believe all of them rely on symmetric keys, which is again why the push for quantum key distribution may become important, so that you can securely move a symmetric key across the spectrum and know that it'll get there securely. And if it gets intercepted somehow, it'll be detected. So you can either keep doing it till you get a good key, or pick a different route or a different mechanism or something.
Okay, and then there's the matter of signatures. I mean, signatures are really more important than encryption, and quantum key distribution doesn't have a good way of doing signatures.
I can't speak to that one, but they are generally well, I don't know. It depends on which modal, but they do have specifications for quantum signatures. I mean, quantum resilient signature algorithms. I'm not as familiar with those, however.
Okay, well, I just, my personal opinion, I don't think there's any future to any of that stuff. It's so complicated. It's so difficult. It reproduces something that we have good technology for already, and I just don't see how it's going to be any better, even if it does work.
Reactions?
Are we, Roger, are you at the end of your presentation?
I'm close to.
Okay.
Listen, are there other questions? I mean, I can take more questions if you want. I mean, I don't really. I have a few other things I want to say. I want to say some of these computers now are just generating like, you know, randomness, and you know, I just want to say how randomness is kind of quantum key distribution is kind of like distributing randomness, but really randomness is like another solved problem. You know, you can generate randomness. You can, I mean, every whoops, our operating systems, the CPU in your machine has a random number generator. You can just
Pseudo random. Wait, whoa. That's pseudo random. That's not random.
Yeah, it's the same thing. It's the same thing.
Wait a minute. Actually, Raspberry Pi's, their random number generator is based on a white noise generator. So it might be about the only computer that has something that is remotely close to true randomness. But it's only used for pulling seeds because it's not fast, and then your seeds go into pseudorandom generators.
Right, and other processors do do something similar, but I mean, I don't know. I mean, I guess I don't think there's really a distinction here. I mean, you know, if so supposedly a random number that comes out of a quantum process is truly random, but if you toss a coin, that's not truly random. Is that what everybody believes? I mean, I don't really accept that. I mean, you have so
I think I've asked about this, and the true randomness of measuring a qubit is supposed and believed in by everybody, but not proven. And the coin tossing is more a matter of chaos than it is a question of randomness.
right, but let's take the most random thing you can get from quantum mechanics. That might be like a Geiger counter reading on a piece of uranium, okay? Because that decay, that radioactive decay is some quantum process. The exact timing of that is unpredictable, but you know, who knows? Maybe if you somehow knew the complete state of those uranium nuclei, maybe you could predict it somehow. You know, I don't know. I mean, maybe that could be some kind of chaos thing also.
Well, supposedly the decay, a radioactive decay, is random in the sense that measuring the state of a qubit in uniform superposition is random, and that's supposed to be truly random.
Supposed to be.
Well, you know, there's a real question is how do you prove something is truly random? As opposed to,
I don't think
as
you
opposed
can.
to, I mean, you assume that a pseudo number random generator is pseudo random, and it's probably random enough for most practical applications, but an attacker with enough resources supposedly can figure out what the pseudo random pattern is. I'm not sure I believe that, but that's, you know, but there's, you don't have to prove pseudo randomness. It is proven, or it is accepted because it's generated via an algorithm. But how do you prove, or how do you measure the probability that you have a truly random source? And some of the quantum computing companies who were selling quantum random generators got into a little bit of trouble over that. So uh, that that would be that would be an area of skepticism I would buy into.
Well,
Because
there has been mention.
they didn't prove to anybody's satisfaction that it was true randomness.
No, I why would you? You might as well take that Raspberry Pi with its thermal process or whatever it's doing, or just get your video camera and wave your hands in front of it and record that and hash it or something. That's going to be as random as anything.
Or a bank of lava lights.
Or a bank of lava lights. Yeah, those are. So I mentioned this possible application of quantum computers. There is a proposal to have a quantum computer produce some kind of like certified random number that everyone could then agree was random, but it's not really practical.
You slept through most of it.
No, I've heard most of it, I think.
So yeah, I think it's interesting to compare quantum computing to other things that have been hyped: fusion power, AI, self-driving electric cars. I don't know. In the case of AI, it was all hype, as you say, it's all hype for a long time. But you know, they're producing real results. Fusion power, I don't know if they're ever. I don't know if fusion power is ever going to do anything practical, but at least we know that fusion bombs exist. We do know that energy can be produced that way. In quantum computing, I don't think we really even have any proof that like you can get super Turing computing results. So let me see if anything else I skipped here. Oh yeah, I said this on many worlds. So Scott Aronson, he gave this amusing answer. Somebody asked him, "Why do you talk about many worlds? You know, many worlds doesn't make any sense. You can't prove anything. You can't do anything with it." And here's the answer he gave. He said, "Well, I don't know. Can you read this?" He said. He says, "Well, some smart people believe in it, so you know, and there must be nothing wrong with it." And then he says, "There's a simplicity of the theory. If you just assume everything happens and you don't rule anything out, you have kind of you have a more conservative theory. You have you have like a simpler theory." Um, and then here this one really got me. He says, "You retort that it's just math. There doesn't have to be any picture of reality behind it. Sounds just as dumb as when the church said the same to Galileo about heliocentrism." You know, and then he says many worlds helps, he uses it in his class because it helps his students understand quantum computing better. Okay, I was getting on this. This is a little philosophical. Free will. I kind of think this relates to some of these issues relate to free will. I mean, you have like, you know, there's like some views only intellectuals and schizophrenics can believe in, and that's parallel worlds and denying free will. You can't really believe in many worlds, or you know, your world would be meaningless. And you can't really. I mean, you can intellectually deny free will, but you really can't live that way. So there's this argument against free will. So it goes like this: if you believe in science and reductionism and all that stuff, and that free will is a natural phenomenon, then the world must be fundamentally unpredictable. And determinist experiments would show errors. And if you go down to the atomic level, it would show electrons that seem to have minds of their own. But I say that's exactly what we do see. You do go down to the atomic level, and electrons do seem to have minds of their own. And we might be seeing this in these quantum computers. When these quantum computers, they really have to have this gate fidelity of extremely high accuracy, extremely low level of anything unpredictable going on, and they have to do this to many decimal places, and it may just turn out to be impossible. It may just turn out that, you know, nature cannot be controlled to that kind of level. There's some kind of low level unpredictability to nature that we just don't understand, and the quantum computers are going to run into that. I don't know. It's kind of a philosophical point here. Anyway, we're near the end here. Does anyone else have any questions?
I just want to put in a plug for my point of view, which is this stuff is fascinating. And I tend to lean on the theoretical side, which means that when students ask me, what good is this stuff? Are there commercially viable applications? I say, would you ask the same question in an art history course? I find the elegance and the mystery of these things to be just overwhelming and exciting. And so it never bothers me if these things can be done actually or not done. The fact that there are small experiments that are proof of concept is enough for me to get excited about them. Just putting in my 2 cents.
Okay, I think like Scott Aronson would say something similar too. But I mean, there's tens of billions of dollars being poured into this. I mean, within the next 5 years, they're either going to get results or it's going to all come crashing down. I don't really. It's not like art history in that sense. It's not just something that a few academics will work on quietly. No, this is gonna score big or it's gonna crash big.
Other thoughts before we close up shop? Roger, I assume you're at the
I'm
end?
not sure what you're referring to when you say before we close up shop. Could you clarify what specific business, project, or activity you're asking about?
Something AI just asked me about that. What the hell? Okay. I don't know what agent was talking
Who
to me
took
about.
who took their leash off their AI?
That's a good question.
That's great.
I'm not sure what you're asking about. Can you clarify what you need help with?
Okay, that's not one of my AI devices.
All right, somebody, some wise guy hooked up an AI agent to us.
Sorry,
Yeah.
what
I
was that?
think I think it's some.
I'm gonna mute all and then unmute you, Roger.
Okay.
Yeah, there you go.
Well, if you believe in many worlds, I think this presentation is just going to go on forever. I mean, you're going to make a decision to disconnect it or something, but in another world, it'll continue and it'll just go on forever.
I'll never get my exam grading done tonight then. The students will appreciate that.
In a different world.
Right.
In another world, yes.
I do have a question. Well, it was an interesting presentation. My question is more in theoretical physics and just to see people's perspectives. And we went over quantum entanglement. So I'm curious about temporal quantum entanglement, meaning a particle that is entangled with a particle forward in time, right? Which
Yeah,
string
that's kind of
theory.
wild. I mean,
String
and
theory
then
will
you're
have
going
to
to use
come
that
in.
to predict the future or something.
Yeah, I want it for stock market.
Stock market. If you had that, you picked the lotto numbers. Jeez, what's the matter with you people?
Okay, true. Okay, okay. Actually, wait. There's more. Okay, actually, no, it could still be done. But the way I thought about it, you first need a quantum server, and then if you do have temporal quantum entanglement, whatever you put in a quantum server, so it could work for anything, political outcome or anything, right? It's pretty much you would have control over the multiple worlds situation, and then it would open, hundreds of paradoxes based on either knowing thinking the future, which might realize it, prevent it, or you might just be completely wrong and like going crazy over it, hysteria. So yeah, I mean, my take in terms of realizing that if there was some path towards it, obviously you would scientists would first have to try a delay of a second, at a minute, and so on and so on, and then gradually increase. And in terms of it, how you're gonna get the same or similar particles that started from the same event as aka entangled at different points in times. The only thing I can think about is either black holes and white holes, with the Einstein's field equations, which is pretty much almost, it's just not feasible. You have to go to space and then it's not provable. Or still using relativity, possibly a hadron collider, but I think that might still not be good enough. Perhaps a journey in space and then coming back, etc., etc. So
So
there's a lot of room for creativity.
I haven't really heard of this concept of temporal entanglement, and specifically not related to quantum computing. Is this just something way out on the horizon in theory land, or?
I mean, people are definitely gonna research it. You can look up temporal quantum entanglement, and you're gonna see papers on it. Most likely, hypothetical theory, initial proposals.
I don't know about that, but I mean, there's a long list of wild theories like that. I mean, there's theories about wormholes. There's theories about closed time-like loops. There's theories about, the future changing the past, or
Yes, wormhole would
a long
definitely
list of things like
explain.
that. All I can say is somebody demonstrates any one of those, and there's a Nobel Prize for them. Okay, I mean, prove one of these really way out theories, and actually demonstrate in a lab, and you're going to get a Nobel Prize. That would be a big deal.
Yeah, yeah. If only it was a bit more feasible. If you are familiar with Einstein's field equations, then it does go over black holes and white holes and wormholes in between, and also goes over parallel universes at the extreme, which you have to kind of like go into a black hole, and then supposedly you would go into a wormhole and etc., and then parallel universes and anti-universes. But yeah, maybe it's just more of a movie plot for now. But I'm definitely curious to hear any perspectives on. It definitely takes some creativity, just even to pitch some potential possibilities there. Uh, so yeah, I think string theory might be also very relevant here.
Okay,
I want
well,
to hear from Barry.
phrase it in the right way, and you might get $1 billion of funding for your company to commercially exploit it.
Sure, thank you. It just takes a white paper, a pitch deck, and then the rest is just finding the scientist. And it's just invaluable info if it was somehow. Look all these $1 billion companies.
Any final words, Roger?
We're all going to get rich, right? I think Brian, everybody's going to take a commission. Everybody who's here visiting tonight.
A commission?
A percentage. We'll all take a percentage.
Royalties just from
Well,
hearing the idea.
Just from having listened.
Okay.
Listen,
Hopefully we're in the right world.
if you want to make money, those quantum stocks, they're jumping all over the place. If you believe in it, buy the stocks. If you don't believe in it, short the stocks. Some people are going to make money off of this.
Yeah.
Okay, Ron, go ahead.
There's too many reasons for stock prices to change, so you can't put any meaning into a lot of that. But yeah.
Personally, I'd rather throw money off of a cliff, but that's just my taste. What other questions or comments do we have before we bid Roger adieu?
I just wanted to say that this was way more interesting than I thought it was going to be. It's just my bias, but there's lots of things to explore here. I mean, there actually is reason to be skeptical about a lot of the quantum technology that's out there, even though it could be demonstrated to do something. Can it be demonstrated to do something that's of practical use? There are, in my experience, I've been able to make a particular type of quantum computer get some work done, but it's a very limited problem space. And early on in your presentation, Roger, you talked about quantum advantage and quantum supremacy. I think they have happened, but you have to put asterisks in against all of them. You mentioned D-Wave's paper, where what they claim to have done is they solved a chemistry problem that has, as of to date, not been solved by anybody with any computers. Is that supremacy? I'd say yeah, but you still got to put the asterisk next to it, because how much effort did they put into solving this one particular problem? And it's pretty clear that the solution isn't general purpose. It probably doesn't work on the the next chemistry problem, but they solved something that nobody else did. So is that the definition of supremacy? And the definition of advantage is, especially in the realm I've been working in, the problems have degrees of, the solution to problems can have degrees of quality. If I can produce a solution with a quantum computer that has a higher quality, I don't care about supremacy. I just can show that I had a small advantage, and if it's a big enough problem, the small advantage can turn into large savings for a client. So, but again, I just want to say this has actually been a fascinating talk, and I really appreciate the thought-provoking dialogue. Thank you.
And I want to thank Roger also. I'm really happy that you accepted my invitation to come tonight. It's been a fascinating discussion, I must say, and we got more chatter on our board, on our message board for this talk than for any that we've ever had before, which is a great thing. I love chatter. I love it when people are exchanging ideas. And now, you know what I have to do? I have students who want their quantum computing exam papers back tomorrow morning.
Yeah.
So I'm going to have to go and grade those now. And, I won't tell them that quantum computing is useless. I'll just tell them, here are your grades. And hopefully they'll all be happy. Okay. So Roger, again, thank you for a really, really, really exciting and interesting discussion. Thank you, everybody, for coming.
Okay. Well,
We'll see you
thank
next
you.
time.
Thank you for letting me go into this little rant.
Rants are always good.
Yes, thank you.
I've learned that controversy sells. So good job, everyone.
Yes, thank you. Have a
Good night.
See ya. Bye.
Okay. Bye.